All right, hey folks, we're back. 3 more limits, 3 more functions. You'll notice all the functions are piecewise defined functions. You gotta know your piecewise defined functions. So let's go at it, shall we? The limit as x approaches 0 of the absolute value of x over x. What's the limit equal to? I don't know. All right. Look at this function. It is a piecewise defined function. How do I know that it's got an absolute value? And an absolute value is inherently piecewise defined. So, if I asked you what the piecewise breakup of absolute value of x is, you would tell me negative x when x is less than 0 and positive x when x is greater than 0, right? Now all you have is a above x added to there. So you got above x, above x. You see that? So you have 2 pieces in your piecewise defined function here. Don't worry about that middle piece for now. Not important in this example. Negative x over x, what is that? Negative 1. X over x, what is that? 1. Now it's a very pretty piecewise defined function. And here I've shown you the graph. This is the constant linear function f of x equals negative 1. It's this function right here. But only when x is less than 0, so open circle. And the constant linear function f of x equals 1 when x is greater than 0. That's right here. You've had this function before. You've actually seen it on a quiz before. All right. But these limits, these piecewise defined functions where we're taking limits, we're supposed to be doing them algebraically in this chapter, not graphically. So this is just there to kind of help you get an idea what's going on. But let's do it algebraically. You don't need a graph. The limit as x approaches 0 from the left. Which piece am I going to use? From the left is clearly this piece. So this is the limit as x approaches 0 of this constant linear function negative 1. Well, constant linear function, it's going to be negative 1. As x approaches 0, negative 1 approaches negative 1. As x approaches 0 from the right, which piece am I going to use? Top or the bottom? Bottom. Okay, constant linear function 1. It's a linear constant linear function, so x approaches 0, 1 approaches 1. Are negative 1 and 1 the same? No, therefore does the two-sided limit exist? No, not at x equals 0. So we write d and e does not exist. We don't write undefined, we write does not exist. That's the common speech in limits. Now we come over to the second function. The second function is the function s, and it's piecewise defined. What type of function is the first piece? A square root function. Well, what's a square root function look like? You know, looks like this. You memorized it, right? In fact, this is the square roots of t with a minus 4 inside the function. What does that do to the function? Shifts it to the right by 4, which is why here's the square root function shifted over to the right by 4. This is a linear function with a vertical intercept of 8, somewhere up about here, and a slope of negative 2. There you go, that's that. Now, please notice there's an open circle here. Why? Because t is greater than 4 for that piece, and t is less than 4 for this piece. It doesn't even talk about what's happening at t equals 4. In other words, what I'm saying here is the domain of this function, the way I've written it, is all real numbers except 4. There's just a hole right there. All right, you can clearly see what the limit as t approaches 4 of s of t equals in this case. It's 0, I think you can see that, right? As t approaches 4 from both directions, what is x comma y doing? All points on the graph. So as as t approaches 4, s of t seems to be approaching, y seems to be approaching what? 0. You can see it. But again, in this section, we're supposed to be doing these problems algebraically, not graphically. So while that helps you, you should be able to do this analysis purely algebraically. So first you got to ask yourself, what's the limit as t approaches 4 from the left? Well, as t approaches 4 from the left, which piece am I going to use? Top piece or bottom piece? Clearly bottom piece. See? T is less than 4. Approaching from the left. So you use 8 minus 2t. How about as t approaches 4 from the right, which piece? Top or bottom? Top. Clearly t greater than 4. Okay, so I use the square root of t minus 4 function. Now, let's see what happens. As t approaches 4 from the left of 8 minus 2t, how do I handle this algebraically? Just plug and chug. Stick in 4 and you get 0. Again, for the right-hand limit, what do? Plug and chug. Stick 4 in here and you get square root of 0, which is 0. Left-hand limit and right-hand limit both 0, therefore the limit is 0. Notice I never had to use the graph. Never had to use the graph. I'm putting the graphs in there because you should be able to translate piecewise defined functions to graphs, and it might help you in your homework or your analysis, but you should be able to be doing these thinking purely algebraically at this point. All right, this is a weird piecewise defined function, but it exists out there. People know about it. It's in most textbooks at your level. It's called the greatest integer function. And here's what a greatest integer function is. You know what a function is. It's a machine. It takes in an input, it sticks out an output. A washer machine takes in dirty clothes, spits out washed dirty clothes that we nickname clean clothes. A greatest integer function takes in any real number and spits out the integer that is smaller than or equal to the real number that went in. The greatest integer, in other words, the integer right below the real number that's come in. So if you stuck in 1.5, the largest, the greatest integer just below that one is 1, so 1 comes out. If you stuck in 13.9, the greatest integer that would come out would be 13. If you stuck in negative 1.5, the greatest integer that is smaller, that would be like negative 2. All right, I think you get the idea. So understand, it's really a piecewise defined function. It's a bunch of constant linear functions is really what it is over different portions of the domain. I tried to draw a representative set here. I mean, it'd be infinite in both directions of this set, but I put in 5 pieces here for you to see. Think about it as f of x equals 2, a constant linear function, when x is between 2 and 3. Where 2 is greater than or equal to x, which is less than 3. What is this saying? If I put in any x value between 2 and 3, inclusive of 2 but not of 3, so let's say a number like 2.5, right? That would be in this part of the domain. If I stick in 2.5, what dependent value will come out? 2. If I stick 2.5, out comes 2. Is that smaller than 2.5 but an integer? Yeah. Is that the greatest integer smaller than 2.5? Absolutely. You understand how the greatest integer function works then. Let's say I put a number between 0 and 1, like the number 1.1. What will come out? 0. So put in 1.1, out comes 0. I think you understand this now. I drew a graph here. I mean, the graph will keep going on and on and on and on that way, like a bunch of steps. It looks like a step function. Right? Greatest integer function is a step function. But here it is. Again, let's try a number like pi over 2. Pi is 3.14 approximately divided by 2. So you're talking about something like 1.5, 1.6, something like that. Okay, so let's take a number like between 1 and 2. If I stick it into this function, what number comes out? 1. Is that what's supposed to happen? Yes. Do you see how this is the graph? Close circle, open circle, close circle, open circle, close circle, open circle. Again, in this section, in 1.6, we're doing limits algebraically, not graphically. So you could ignore the graph entirely and go from here to here. The point is you have to rename this nicknamed function. That's just like a shortcut, a shorthand way of writing the greatest integer function. Here would be like a longer way of writing it. The limit as x approaches 3 from the left. As x approaches 3 from the left. So which piece am I going to use here? X is approaching 3 from the left. All right. Well, we're going to have to use something like 3 from the left. We're talking about some number like 2.9, something like that. So what should be spitting out? 2. So clearly we're using this piece right here, which makes sense, right? 3 from the left is something between 2 and 3. And 3 from the right, well, that would be, it's not even on here, but it would be 3. And because these are constant linear functions, as x approaches 3, 2 approaches 2. As x approaches 3, 3 approaches 3. All right. Therefore, what we say about the limit as x approaches 3 from both directions doesn't exist. Thanks. And now presenting
the squeeze theorem.
That's right, folks. Today we're going to be looking at the squeeze theorem. This is the basic idea of the squeeze theorem. If I have some function g that is for all real numbers between a function f and a function h, see g, which is right here, is between f and h. If I know the limit of f at a value, say pi over 2, and I know the limit of h at that same value, pi over 2, and if they're the same limit, then the limit of g at pi over 2 also has to be the limit that f and h are. That's the squeeze theorem. All right, so let's take a look at this example. What type of function is f? Quadratic function. Its graph is an upward parabola, in this case shifted over to the right by pi over 2, and you can see that. What type of function is this? An absolute value function, which is the function that looks like a v. It's shifted to the right by pi over 2. And then the negative in front of a function does what to it? Flips it over the x-axis. And so we get this right here for h. Now look at g of x equals 0. That's just the constant linear function with a slope of 0 that runs through the origin. That's this function right here. Now we could calculate this guy's limit, no problem, right? But this is for demonstration purposes. If I want to calculate the limit of g as x approaches pi over 2, I can do that by calculating the limit for f as x approaches pi over 2 and the limit of h as x approaches pi over 2. And if they're the same, that's also the limit as as x approaches pi over 2 of g. All right, so we see that over here. The limit as x approaches pi of 2 over 2, well, what's it going to be? No problem. Plug in pi over 2 and you get 0. 0 squared is 0. How about h of x? If I plug in pi over 2, and for h of x, what do I get? Negative 0, which is 0. The limit as x approaches pi over 2 over f of x is 0. The limit as x approaches pi over 2 of h of x is 0. So what must the limit as x approaches pi over 2 of g of x, the function between f and h, be? That's right, 0. That is the squeeze theorem. If you can't, for whatever reason, algebraically calculate this guy's limit, but you can calculate this limit, and you know that they're going to be the same, you have got the value of this function. Fair enough? All right. And we know this to be true, right? As x approaches pi over 2, what is g of x clearly going to approach? Well, it's always going to approach the same y value, which is 0. Right. Let's try this more interesting example. If I asked you the limit as x approaches 0 of x squared sine of 1 over x, this is a product of functions, you may or may not know what that function looks like. We've seen it before. It's the one that kind of looks like this and then gets really small down to a dot and then kind of does this again. But we're not approaching this graphically, we're approaching this algebraically. So I really don't know what this limit is. Let's try approaching it. Let's try looking at it algebraically. I plug in 0 over here and I get 0 times sine of an undefined number. What in the world is sine of undefined? That's not even a thing. So I'm like completely confused by this like mess. All right. So what if instead I said, okay, this is got to be the middle function if I'm going to use the squeeze theorem. So I'll call it the middle function, g of x. G of x equals x squared sine of 1 over x. Then I say, what's a function that's always greater than that? Well, it's actually really easy to make because sine of 1 over x, sine of a, sine of x, sine of q, sine of dog is going to always range between what two values? Negative 1 and 1. So, leaving the x squared in place, but setting an upper value for sine of 1 over x of 1 and a lower value of sine of 1 over x of negative 1, because this guy's going to go between negative 1 and 1, I know this function is always greater than this for all real numbers, and this function is always less than this function for all real numbers. So here's my hope, that this function f of x equals x squared and this function h of x equals negative x squared, that I can compute their limits at x equals 0. So let's see if we can do that. The limit as x approaches 0 of x squared is, well, clearly just plug it in, you get 0. The limit as x approaches 0 of this function, which is negative x squared. Negative x squared is clearly negative 0, which is just 0. This function's limit as x approaches 0 from both directions is 0. This function's limit as x approaches 0 from both directions is 0. Therefore, what must this function's, the g functions, the limit as x approaches 0 of the g function be? The answer is 0 by the squeeze theorem. Okay, that's the end of section 1.6. A lot of algebra in there. We've talked about we've talked about limit laws, we've talked about algebraic manipulation of functions to get them to be usable. We've talked a lot about piecewise defined functions, taking limits of piecewise defined functions. And we've even talked about this crazy thing called the squeeze theorem, which in practicality you only use once in a while, but you need to know it. All right, good. Thank you.